Welcome to Advanced Data Analysis 2 with me, Erik Erhardt, Professor of Statistics at the University of New Mexico. In this video, I hope to get you started with class assignment number 5, a taste for model selection. So we'll start looking at multiple regression and how to select an explanatory model that is as simple as possible, basically using Occam's razor to find the model that is complicated enough to capture the main features, but not too complicated. So I will start by downloading the R Markdown file into my ADA folder and the data file. And I will also open up the HTML file. All right. Let's take a moment before we look at the assignment. Let me just read this into RStudio. Let's see, desktop, ADA2, and the Markdown file. Okay, we'll set the session's working directory to the source file location, and we'll knit. All right, so while that's working, let's take a look at this assignment. All right, so we have from the California Child Health and Development Study. It's a fairly old study. It involved women on the Kaiser Health Plan who received prenatal care and later gave birth in the Kaiser clinics. The total data set has about 19,000 live-born children out of 20,500 pregnancies, and we're considering a subset of 280 babies who were born. These happen to be white male infants, and I keep looking for another subset of this data, and I apologize that I have not yet done so. This is a data set I inherited long ago. Data were collected on a variety of features of the child, their mother, and their father. So the columns in the data set are all of these. We're not going to look at all of these variables, but we have an ID column. We have child's head circumference, child's length, and birth weight. It's the birth weight that is our main response variable here. We have the number of weeks of gestation, the mother's age in years, how much she smokes in cigarettes per day, the mother's height and pre-pregnancy weight, and then the father's age, education, smoking, and also their height. And we want to know whether there's a subset of these variables that helps predict a child's birth weight. So we start by loading the tidyverse functions, loading the ADA functions script, and then reading in the data set. So we read the data set in, and now the read CSV function uses the first 100 or so rows to try to identify what the data type of a variable is. And for a lot of these, because the data are sorted, I believe, for some of these columns, it doesn't identify that they're numeric because all the values for the first 100 or so columns are all zeros. And therefore, the function sort of interprets all zeros as being, well, maybe this is categorical, and 0 is one of the levels of this categorical variable. So we actually need to manually tell it that actually this is a double, meaning a double precision numeric variable. So we assign those column types manually. So I guess this is sort of a nice thing to see so early in your career, that sometimes these files that read data in and automatically format the columns by their data type can make mistakes, and that there's ways of overriding that so that they're interpreted correctly. All right, we're only going to keep these variables. So we have the child's birth weight. We've got a set of variables for the mother, all beginning with M, and the ones for the father begin with P. So we're looking at the age, smoking, height, and then for the mother we've got pre-pregnancy weight, and for the father we've got education. So can these help us predict a child's birth weight? This piece of code here that's commented out, this can be used later on to exclude certain observation numbers. Slice is a way of like taking a slice, selecting certain rows from a data set, and the minus sign means that we're going to exclude that row. Okay, so this isn't in play yet. We're just showing you an example for later on. All right, so we've got our subset of data. We've got 680 observations. We have these 9 columns. There they are, and we're ready to go. I don't see all those leading zeros here. I don't know what the problem would have been earlier, why we needed to specify this. I would need to run this code without this column types. Maybe you could do that and see what happens. All right, onward. So here's the first 6 rows of the data set. We've got child's birth weight as the first variable. That's nice. In the scatterplot matrix, we'll make sure that this is the first variable in their scatterplot matrix so that it appears as the y variable compared to the rest of them, which would be x variables. All right, here are the 6 steps of this assignment. The goal is to build a multiple regression model to predict the child's birth weight from the data on the mother and the father. A reasonable strategy would be to first examine the relationship between birth weight and the other predictors. We're going to do that and also look at the relationships between predictors. Second, decide whether any of the variables should be transformed. Maybe there's a nice curved relationship that we should consider transforming one of the variables. Third, perform a backward elimination or backward selection using the desired response and predictors. Okay, so just start with the model that we have. Fit a full model, assume that that full model is correct, and then do backward selection to see if we can simplify the model without any substantial reduction in explanatory power of the model. Then, given the selected model, examine the residuals and check for influential cases. So examine the residuals, meaning check model assumptions. And if all that works well, then we sort of can skip step 5. But if there's things to address, like issues with the residuals, so violations of model assumptions, or in cases that are too influential, and maybe we want to assess whether how much the model's fit depends on those influential cases, we might remove those and then repeat this process. And then when we're happy with our final model, finally we'll interpret that model and discuss any limitations. All right, off we go. So we'll start by looking at the data. First, we're going to answer the questions: describe any patterns you see in the data. Are the ranges for each variable reasonable? This question is often overlooked. There are things that you know about the world. You may not be an expert in a particular data set, but you know maybe something about people's heights, how many cigarettes they might be able to smoke, things like that. And so it's worth just putting your intuition to bear on each of these plots to see if what we're seeing is reasonable. Are there extreme or unusual observations? Are there strong nonlinear trends with the response that suggest a transformation? So here's a summary of the values. So all right, so if I shrink this, will it all fit? Yes, good. So child's birth weight are between 3 and 11 pounds. That seems like a reasonable range to me. This, of course, is very low here. These are probably preemies or, anyway, I don't know that much about child birth weight, but let's see, mother's ages from 15 years old to 42. Okay, that's seems reasonable. Smoking can be anywhere from 0 to 50 cigarettes per day. Okay, mother's height in inches, 57 to 71. That seems reasonable. Father's weight, the mother's pre-pregnancy weight, 85. up to 246. Those seem fine. Ages, so now the father's age, 18 to 52. So yeah, fathers can be a bit older than mothers. Smoking, congratulations, fathers smoke as much as mothers. Fathers' heights from 62 up to 79, okay, and education from 6 to 16. All right, so all those ranges seem to be about right in terms of my intuition. All right, we're going to create the plot here, and we're making the upper diagonal be the points and the lower diagonal be the correlation values. And so the child's birth weight is the first row and column. And so if we look across this first, let me zoom in a little bit, this first row of the plot, we see that with respect to mother's age, it doesn't look like there's much relationship. In fact, all of these sort of look a bit weak. It looks like maybe there's a slight positive for mother's height. Pre-pregnancy weight, maybe not that much. It does look like, there aren't that many mothers who are like really heavy. Most of them are sort of this average, I'd have to go down and look at the scale, what's sort of down there. Sort of between 100 up to 200 or 175. Looks like 175 is sort of where most of the mothers end. So it's sort of unusual for mothers to be heavier than that before they are pregnant. The father's age, smoking, maybe slight positive with father's height, and education, maybe not much. It's really hard to see that there's strong relationships here. One thing I'm happy to see is that father's age and mother's age is positively correlated. Okay, that's good. There's quite a bit of spread there, but that's, anyway, those are real relationships. Let's see, mother's height and pre-pregnancy birth weight, there's a positive relationship. So the data are making sense to me. In fact, even with father's height and mother's height, this one here, it looks like there's a bit of a positive relationship. So not that much. It's quite a bit weaker than age. But all right, some of the correlations that stick out as strong. Here's a 0.8. That's the father's age and mother's age for sure. Yep, 0.8. If we look over here on this first column under child's birth weight, this is the correlation between child's birth weight and mother's age. And then this is child's birth weight and mother's smoking. So there's a negative correlation with mother's smoking, positive correlation with mother's height, positive correlation with pre-pregnancy weight, basically no correlation with father's age, basically no correlation with father's smoking, positive relation with father's height, that makes sense, and education, maybe not much of a relationship there. So, okay, so some things are making sense. Here's sort of another version of that correlation matrix, and these are the p-values associated with tests for the correlation. And this first row or column shows where there are significant correlations. So definitely for mother's smoking, mother's height, pre-pregnancy weight, and father's height. Those are the four variables before we've done any modeling that seem to have some association with the child's birth weight. The other ones so far are not important. Now, it's quite common, well, not, I don't know, it happens that a variable that is not important by itself becomes important when other variables are in the model. So I wouldn't rule these other variables out yet. Instead, that's what we're going to do when we use backward selection. So some of those observations that we saw in the plot, go ahead and note them down here in the solution. All right, let's move forward with backward selection. So one of the assumptions in regression when we're comparing models, as we're going to start with a full model and we're going to make the model smaller. The main assumption is that the full model fits the data. So we're going to first fit a full model with all the variables. That's what this is here. And then we're going to assess the model assumptions and make sure that that full model fits. And if it does fit, then we can reduce the model and assess that the reduced model also fits. If both of those endpoints fit, then probably all the models in between fit. We're sort of making an assumption there. And that the only real difference between the full model, which fit the data, and the reduced model that still fits the data is that we have a simpler model, but it still explains most of the variability that the full model also did. All right, so that means that we're going to fit the full model and check model assumptions first. So here's the child's birth weight relative, and we're related to all the other ones. We put that into an object linear model, CCHD, that's the data set name, full for the full model. And we're going to look at a summary. I'm sort of going to skip over the summary except to say that the proportion of variance it explains is 10.4%. Okay, not very much. Child's birth weights seem like they're going to be hard to predict from these features from the parents. All right, let's look at the diagnostic plots. And I think, let me page down for just a moment. Model selection starts here. Keep paging down. Okay, that's the reduced model. Okay, I just want to put in mind what we're going to be answering. So discuss the diagnostics in terms of influential observations or problematic structure in the residuals. So that's sort of model assumptions. In particular, if an observation is influential, describe how it is influential. Does it change the slope, intercept, or both of the regression surface? Okay, so we're going to keep that question in mind. I'm paging back up. And okay, so there's not that much to answer for this part of the assignment. I think I let you off a bit early, a bit easy. But let's start here. So the QQ plot shows that our residuals are basically normal. We have a few points out here that are beyond the bars, but this is a fairly minor departure. When you have larger and larger data sets, you very often have a few points on each tail that sort of go outside of the bounds. And because the data sets are so large, a few observations like this rarely have much of an effect. So this looks pretty good so far. In terms of influential observations, it looks like 506. Observation 506 is something that we're going to maybe have to look at. It's a little over twice as big as the next few observations that are influential. So let's return to this observation a little bit later. We see that its high influence is not that much because of high leverage. There are some points that have extremely high leverage but are not influential. Right, high leverage, it's far out on the right for the x-axis, but it's down low for the y-axis. So that's good. Yeah, I mean, 506 is in sort of in this right tail of all the point. Most of the points are below, so it is a bit of a high leverage point, but not as big as several other points that we see. These residual plots look totally beautiful. No real structure here, just a big blob. So this is for the fitted values. This is for mother's age, mother's smoking. So notice mother smoking, how there's sort of these vertical bands. That's because people smoke. It's likely that in the survey this was sort of grouped questions like zero cigarettes, 0 to 3, 5 to 10 or something. I don't know, and they sort of average in these ranges. So it's probably why we're getting these ranges. It's interesting that I would sort of expect a band at 20, a band at 40, which would be like 1 pack, 2 packs. But it's just how the data came to us. All these residual plots look totally great. No real structure with mother's height, mother's pre-pregnancy weight, father's age, father's education. Here's some of those influential points, I think, because they're a bit outlying with low education fathers. Father's smoking, father's height, all those look great. the Box-Cox plot suggests that we transform the y variable with a power transformation equal to 1. That means leave it like it is. So that's great. Added variable plots, we're seeing observation 170 sort of has a large residual. We're seeing sort of no relationship with age, a slight negative relationship with mother smoking. Okay. Here's observation 506. That's the one that has high influence. It looks like it's sort of counteracting, right? This is a positive slope line, but 506 would be pulling this line down. So it would be reducing the significance of pre-pregnancy weight. Here it's sort of in the middle of the data, really no effect other than maybe bringing the whole line down a little bit. Same thing here. It's a big residual, but not really influential. 506, same thing here. It's in the middle of the data, Let's scroll up just a little bit. Look at these. 506, middle of the data, 506, maybe pulling this one down a little bit, but there's plenty of others that are doing that. I don't see 506 as being that important for changing the relationships in the model. So while it is influential, it's probably because it's has a large residual and just sort of pulling down on the regression surface rather than changing the slope. All right, so those are some of the comments to add there down at the bottom. All right, let's do our model selection. So we're going to use this function called step. We're currently, by default, we're using AIC, the Akaki's information criterion, and we're going to start with the full model. We're going to do backward selection, and this F-test just adds these two additional columns to give you basically like p-values for whether or not a model is significant or not. For each part of output, right, our goal, the best fitting model for this information criterion is to minimize the AIC. So the current AIC is 62, and we want to make it smaller. Okay, so here's our starting model. It's got all 8 predictor variables in it, and the columns here, I don't know, this degrees of freedom, that's how many degrees of freedom would change if you did any of these actions on the left. Sum of squares, residual sum of squares, AIC, that's the main column that we're looking at. We're trying, and you can see that these numbers are sorted by AIC. The top choice here is the best choice, and this will often correspond with the largest p-value and smallest f statistic. That is, the variable that is the least important or least significant in the model is the one that you can drop. These choices down this first column are changes to the model. The minus sign means that you would remove the variable, and father's education is the first one. If you removed age, father's age, mother's age, smoking, you would all do better, meaning you'd have smaller AIC values, than doing nothing, which is, this is the current model where we're at. Okay, right, the 62.758, that's the starting value. So it says that we can do better, we can have a better model in terms of AIC if we drop father's education. So that is the first thing that happens. And if we compare the next model to the one that we started with, the only difference is that there's no father's education. Okay, so we remove father's education, then it looks like you can remove the mother's age and get down to reduce the AIC from 61 down to 59. And then you can remove the father's age to go from a 59 down to 57. Okay, and each time these the significance of these predictors is insignificant. Father smoking, you can go from 57 down to 56. All right, and finally we get to a model where 56 is the lowest AIC. If you remove any other variables, the AIC goes up. So, and it turns out that, though it doesn't necessarily turn out this way, that these are also significant in the model. All right, so this seems like this is our final model for backward selection. So the process stops. All of that, let me page up for a moment. From the step procedure, the result went into an object that I called reduced, red for reduced, and AIC to indicate which criterion I used for that reducing. If I page down now, I'm going to move that reduced model and call it final. And now we'll look at the summary. So I notice I created 3 linear model objects. I started with the full model, and then the reduced model, and then final. And that for me keeps it very clear about what part of the process I'm at for my linear model object. I could very easily just use the same variable this whole time. But you can see sometimes I create more variables than I need, but for the benefit of clarity. All right, so let's look at this model here. The residuals look somewhat symmetric in terms of their 5-number summary, centered close to 0, and the quartiles and the min-max are roughly symmetric. That's good. We're still explaining about a little over 10% of the variability. So we haven't lost that much explanatory power. I think the previous number was 10.34. Now it's 10.16. So we've lost a fraction of a percent decrease in variability explained, but we've made our model half as complicated with only 4 variables instead of 8. So this is quite a good benefit. Looks like as mothers smoke more, the child weighs less, and then the other 3 are positively related. So as the mother's taller and the father's taller, the baby's heavier, and if the mother has a heavier pre-pregnancy weight, the child's also heavier. So all those make sense with what I understand about the world. All right. Let's assess the model after we've now reduced it. All right, so these residual plots, ideally, these residual plots aren't going to change very much. And so we still have normal residuals. It looks like this 506 is more influential than it was before by a little bit. So we probably still want to check that one out a bit. It seems like it's has a little more leverage now too than it used to. All these residual plots look great. I'm not going to spend much time on this. Box Cox looks good. I encourage you to slow this down and look a little more carefully if you like. But 506 looks like it has a little more leverage with this plot, but in the opposite direction, right? It's 506 isn't creating this slope to be significant. It's actually working against us. So I'm even more inclined to believe this relationship holds. This child right here, 506, this is someone who had a much lower birth weight than we expected by about 3 pounds. And contrary to the mother's pre-pregnancy weight, which was much more than average, right? 0 here is the average pre-pregnancy weight. So this mother was heavier than usual, but gave birth to a very underweight child. That's what's happening here. All right. So describe how that unusual observation is influential. I think we've talked quite a bit about this. We don't really think it's going to change this regression surface very much. The slopes, it's sort of reducing the slopes a little bit, and it's changing the intercept by probably pulling the whole regression surface down a bit. That's what I think. All right, so now is a key moment in the model. Let's address the model fit. So if the model doesn't fit well, and the diagnostics will tell you this, that the residual plots don't look good, or the normal distribution doesn't seem to be met, things like that. Box-Cox transformation is suggesting something quite different. Then we should address that lack of model fit. Now we don't really, our model fits great. That's what I'm seeing. I do make a point here that model fit is not about R squared, right? R squared is the proportion of variability that we can explain in the response variable with the model. And that's important for prediction, but it doesn't tell you that the model fits well. The only thing that tells you model fit well is about the model assumptions. All right, transformations and removing influential points are two strategies that we can use here to assess lack of fit. Now, the only real issue that I see is about observation 506. So the decisions you make should be based on what you observed in the residual plots. If there's an influential observation, remove it and see how that affects the backward selection, whether the same predictors are retained, right? Sometimes you remove one observation and your model reduction completely changes. So really key idea here, everything depends on everything else, is something you'll hear me say over and over again. So we started with this full model right here, and then we did backward selection. If we find that a point is influential, we have to go back to the top and start everything over again. So we've got to redo our model selection because our model selection is going to be influenced by an influential point. So just wanted to sort of make that point to you. All right, see how it affects the model selection, the model fit, the diagnostic plots. Have we resolved the issues that we saw in the diagnostics by removing the influential observation? That's what we'll be looking for. And the regression coefficient estimates. So do those estimate, or the beta values, if I page up for a moment, do these estimates change very much if we remove the influential observation? So we'll be checking on that. Page back down. If there's a pattern in the residuals that can be addressed by transformation, guess at the appropriate transformation and try it. Okay, for us, our residuals look great, so we don't need to do that. Repeat until you are satisfied with the diagnostics meeting the model assumptions, and below, briefly outline what you did, no need to show all the output, by identifying what you observed in the diagnostics and the strategy you took to address that issue. Finally, show the final model and diagnostics for that. Describe how the final model is different from the original. In particular, discuss whether the variables retained are different from backward selection, and whether the sign and magnitude of those regression coefficients, the estimates, are different. Okay, so here's the solution. So let's go work on this part. This is the fun part. So observation 506 was a troublemaker. So I'm paging down through a little bit, and somewhere, yes, this is where we are. So basically, the first meaningful code chunk where we read the data set in, we are going to, so we read the data set in. Oh, by the way, let's just try this. I just want to see if we get that weird issue. Oh, I need to tidyverse. Okay, run each of these things. Source. And I wanted to see if we can reproduce this issue with the data types. Double, 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 double. Oh, interesting. See how this is character? CHR? Same thing here, character. So something's strange happening with this variable. Okay, so that's why this additional these additional column type arguments are helping us treat those numerically. Okay, so there's our original data. I highlighted it and pressed Control Enter to submit those lines down to the console. But now we're going to address the observation 506. So I'm going to take this slice code, and I'm going to say 506. Okay, so we're going to exclude observation 506 from the data set. And so I'm going to make a comment too here that observation 506 was influential in full and reduced model. Okay, so that's why we're doing that. So now I need to run this whole chunk of code again. Let's look at the structure. Sorry, I'm not very good at my touchpad doesn't work very well for scrolling up and down, so I have to use these bars. Okay, so we started with a data set with 680 observations, and now we've got 679. So I've just confirmed that the change we made did something. Okay, that's the main thing I was doing. All right, so now let's scroll down a bit. We've got our, okay, we have a summary. We can make a plot. I encourage you to do that. We could probably see, I'm not sure if we can see where that observation is in the original scatterplot matrix. It's going to be hard for this to view in my RStudio window very big, but we're looking for someone who has low birth weight with, we remember, high pre-pregnancy weight. It might be something like this point here, one of these 2 points maybe. Anyway, it's going to be hard to see the difference on that scatter plot. All right, let's look at the correlations. I think that we're still getting significant where we saw it before. So no real change for those correlations. Let's fit our full model. And the same variables are significant in our full model as before. Let's look at the diagnostic plots. So here I'm going to make the plot window a little bit bigger so that we can scan through these. I'm going to go a little bit fast here. We're expecting these to be very similar to as before, just that 506 isn't going to be influential. So the QQ plots look great. 506 is not here anymore. These other influential points, or the degree of influence doesn't look very big here. This looks good. Okay, next plot. Probably shouldn't, it's not going to really change anything for these other residual plots. These all look great. Still box plot, or box Cox doesn't suggest a transformation for the Y variable. Added variable plots, now observation 506 does not appear. Some of these slopes look a little stronger than they did before, a little steeper, because 506 isn't pulling against them. So all this looks great. All right, let's go to model selection. Okay, we'll fit the reduced model, and let's see which variables were retained. Now I need to make this window a little bit bigger. I may need to run that summary code again. Let's do that again with the window full size. Am I nearby? Okay, yeah. Let me just do the stepwise regression again. I'm going to clear the console so that anything in there is only the stepwise regression. Okay, so we first removed father's education, and then mother's age. To my memory, so far this order is about the same. Father's age and father's smoking. And we end up with a model that has mother's smoking, mother's height, mother's pre-pregnancy weight, and father's height. That is the same model that we had before. So good. The coefficients, did the coefficients change? Well, let's see. I still have on the web page, let's see, we can sort of flip back and forth a little bit. We still have the estimates from before. Mother smoking was about negative 0.017, 0.016 for mother smoking, so not really much of a change there. Mother's height, positive 0.045, 0.041 okay, about the same. Pre-pregnancy weight, 0.009, and this is 0.010, so a small change, but not much. And father's height, 0.041 and 0.41. So pretty much about the same. So really, while that point was influential, it did not change our inference in the model. We have about the same, about the same interpretation of each of our coefficients. Multiple R squared, we're actually able to explain more variability now than we could before, and that is true also with the full model. If we page up and look at a summary of the full model, we started at 1094, whereas previously for the full model we had 1036. So that one influential observation, it was an outlier, and it created a lot of variability, enough variability that it was impacting our how much variability we could explain in our response. So we can do better now. Let's see that we've done. We haven't looked at the diagnostic plot for the reduced model. I'll just say that it's just as good as the full model. They look great, but definitely spend a moment to do that yourself. And let's go back to the questions here. All right, so the main comments here are that we have the same variables retained from model selection. The sign and the magnitude did not change very much, so we end up with the same model effectively before and after. And because we removed that influential observation, we can explain more variability in the response, both in the full and reduced models. All right, now interpreting the final model, this is the same as the previous assignment. So I'm going to let you refer back there for interpreting the proportion of variation. So what proportion of variation in the response does the model explain over the mean of the response? Okay, so that's the multiple R squared value. That is the this value down here. So 10.9% of the variability can be explained by this regression model. And finally, write the equation for the final model and interpret each model coefficient. Okay, so our reduced model, full final, here we go, 10.7 is our reduced model. And so write out the model equation. And you know, if I were doing this, I'd do something like I would copy this because those have your variable names. Yeah, let me just sort of do this real quick. Interpret the final model. Okay, write the equation. Here we go. So I would write the equation something like this, and then I would copy each of these estimates in there. So we've got the intercept plus, and you know, do the rounding appropriately. Choose a number of significant digits that you're going to use. And put each of those values in there, etc. I'll finish because I started. Two. Okay, do something like that. And if you can put it in triple ticks if you like, it'll display a little bit better that way. Okay, and then interpret each of these model coefficients as well. And do they make sense? We've already sort of discussed this. We have a negative slope for smoking and positive for the other ones. That sort of corresponds with things that make sense to me. And then to inference to whom? This data set represents a subset of all the births for the California Kaiser Health Plan, and that's a subset of the United States and a subset of the world. So does this actually apply to all humans, or is it a subset? And I'll tell you that this does not generalize to all humans, though you might expect some similarities, that smoking probably causes negative relationships with birth weight overall, and these other things, father's height and mother's height, probably also relate to larger babies if you're taller. But to whom does this actually apply? Well, this model applies to basically the group of people who were sampled. So this is only for live-born white male infants, for people living in California who are on the Kaiser Health Plan, who received prenatal care, right? So all those conditions need to be satisfied for the population, right? So once we fit this model, we can now make predictions of future women and men, because the father's data are in here too, future families for the weight of their child. But we can only predict with 10%. We only explain 10% of the birth variation in birth weight. Anyway, so that is the full assignment. I hope you have a good time with this. This backward selection process is something we're going to see over and over again. This is just an introduction to it, and we'll go into much more detail in a few weeks in this semester. All right, see you next time.